Welcome to our fourth problem session. We're going to be talking about binary trees mostly today. We'll talk a little bit about binary heaps, which is a topic we won't cover until next Tuesday, but it will appear in very small ways on your problem set 4, which will be due next Friday. So I'm going to go over a little bit of that material today. But it's mostly concerned, the subject material for today is mostly binary trees, specifically being applied to set data structures and sequence data structures, as Professor Demain talked to you earlier this week. But for now, actually as of yesterday, you've seen all of the data structures that we're going to cover that will implement the set interface and the sequence interface, right? Those nice tables that Professor Demain has been showing you, right? Those are now complete, right? We have some data structures that are really good constant time operations for some operations, so we might choose them for some applications. And this week, we've been describing to you trees which achieve like really pretty good for any type of query operation on my sets or sequences. Pretty good meaning logarithmic time, not quite constant, but for our purposes, log n is, on your computer, practically, right? Not asymptotically, but practically, log n is going to be at most what on your computer? Something like 64, right? Any input that you're operating on with n machine words as your input, right? You need to be able to address all of those machine words, right, in your input. And on your computer, the size of your machine word addresses is 64 bits, right? And we assume that the word size is at least log in the size of your input so that you can address the input, right? Right, so for your purposes on your computer, log n is going to be no more than 64, which means you get maybe a 50 times overhead, or for smaller instances, it could be more like 10, right? If you've got like 1,000 things that you're working on, right? It's not that bad, right? It's a constant. It's not a constant factor for theory purposes, but for your purposes, log n is much better than a polynomial factor, right? Another factor of n. Okay, so you've seen all the code. You've seen implementations of all of these set and sequence interfaces, right? So I went ahead and wrote I compiled all of that code from your recitation notes of all of the different interface implementations. And what I did was I wrote a little test program to see how they ran on a real machine, right? So I have a little test code here, right? So I have a little folder that lists, an array implementing a sequence, a binary tree implementing a sequence, a dynamic array implementing all these kinds of things, right? Then set things, a sorted array being a set, and a binary tree and a hash table, right? These are our implementations. I'm not using Python dictionaries for hash tables. I'm using the implementations that are in your recitation. And I'm going to run this little test efficiency Python code that basically is just going to, for each one, it's going to do a bunch of these different operations and measure to see how much time it took, right? I'm just logging how much time it took. It's not an asymptotic analysis, but, hopefully we see some separation, yeah? So I'm going to press that. It runs a bunch of tests, so let's take a look. Okay, so I got a bunch of sequence operations, right? We got build, set at, get at, insert, delete at the various places, right? And I'm giving, these are the actual timings to some scale, right? To some resolution that I had for these data structures. And you can see actually build on this machine, just allocating some array and clearing it is a really efficient thing that Python's going to do for me. And so that's actually, it's mislabeling that as log n, right? But these other things, get at and set at, really, really fast, right? That's constant time. And then these other things I essentially can't do better than loop through the thing. And so it takes linear time. And again, sequence stuff, setting at and getting at is slow. but deleting and removing from the first thing, I'm just relinking the pointer, right? Dynamic arrays, again, set at, get at is fast because it's just dynamic, it's just regular arrays. And then inserting and deleting last, that's getting me essentially constant time. Now, I'm actually, when I'm running these tests to deal with averages, I'm actually running these things a lot of times and testing their performance. And so I'm not seeing the worst case happen here, right? I'm averaging over all of the things, which is exactly what amortization means. And so that's why I'm getting good performance here. A hash table, again, really, so this is what we talked about in problem session last week, right? Implementing a kind of a double-ended queue with a hash table. This is that implementation. I just want to show it to you, but it's actually pretty good. This is what JavaScript uses for arrays. And then a binary sequence represented as a binary tree, right? A balanced binary tree. This is our AVL code that I had. And you know, all the other things have been really pretty bad at insert at and delete at. But this one does comparable to all the other things. Now you see these are a little bit more, you know, machine cycles than the other things, but, you know, not so bad, actually. And then on the set side of things, again, we had a sorted array. Sorry, this is a set from an array. Basically, it's an unsorted array. I'm just looking for all the things. That's very bad times. Sorted array does these find operations great, but inserting and deleting is poor, right? That's why we need binary trees. Hash tables, you know, get good kind of dictionary operations, but really bad order operations, right? And then the binary search tree, right? A set binary tree, again, does quite good on all of these things. In fact, it's getting really quite good. It's getting better for some reason than the sorted array even did. So I don't know why our implementations are not optimized at all, but it does pretty well asymptotically. Yep?
Could you explain again why the first data structure we looked at, the build time was log n?
Well, this is just labeled based off the timings, right?
Oh.
It happens to be that probably there's a C intrinsic underneath Python that allocates this thing, and so it does it really fast. And so my program that's looking at these numbers and trying to guess what the asymptotic running time is, these are just labels based on these things, ranges. It's mischaracterizing.
It's actually a building at any time.
Yeah, well, I mean, in actuality, if it was C code, right, if all of this stuff was in C, probably we'd see that bar be longer because it's actually having to go through and touch all that memory. It's still doing that here, but all the Python stuff is super crufty, right? It's like 100 times slower than anything that C does. And so you're seeing that disparity here. Does that make sense? OK, so I just wanted to show you that. We might release this for you to play around with, but just wanted to give you a taste of that. OK, any questions before we move on? How do I turn this off? Up and off. Shut down. Yes. OK, so, whoop. All right. So moving on to problems, working some problems. So you have your set of problems here. The first one is we're going to look at a sequence AVL tree. Right, this is a sequence AVL tree. How do I know that? You don't necessarily. But these things are certainly not in sorted order of the things I'm stored in them, right? So it better not be a set AVL tree, right? Is it an AVL tree? Is it balanced, height balanced? Yeah, basically. Actually, if you compute the size of each subtree, right, the left and right subtrees on all of these, you can confirm for yourself, are balanced, right? They're within plus or minus one of each other. Actually, this is about as far away from balance as you could get for this many nodes, while still maintaining height balance, maintaining AVL property, which is why this is an instructive example. It's kind of at the limit, okay? And what am I going to do? This is what's missing in this picture if I'm claiming this is a sequence AVL tree? Any ideas? What's missing? what does the sequence AVL tree store that I'm not showing in this picture? What? Counts and it's a sequence AVL tree. Heights, right? So it's a sequence AVL trees different than set AVL trees are augmented by two things, right? Because I need to be maintaining balance during rotations, and so I need to store heights. I need to be able to tell what the heights of these subtrees are in constant time when I'm walking up the tree fixing things. And the sequence requires me to store their subtree, the numbers there, right? So I don't know, I'm not going to draw it for all of these things, but how about for number 4? What's its height? 1, 2, 3. That's the longest path from the root subtree of that. So this is, height equals 3. That came from height equals 2 and height equals 1. Does everyone see that? Yeah? And then the size here, how big is that? That's 1, 2, 3, 4, 5, 6, 7, right? So this is, I'm going to put size equals 7 here, right? And that's coming from this guy, 1, 2, 3, 4. And this guy is 2, right? So how do I compute the subtree size? It's my left subtree size plus my right subtree size plus 1, right? And my height is taking the max of the 2 plus 1, right? All right, so we did all that yesterday. So I'm just labeling these things. And what I'm asking of you is to perform a delete operation. This is a sequence tree. So I'm finding things by their index in the tree, right? So I'm going to ask you to delete the 8th thing in my sequence. Okay? So what is the 8th thing in my sequence? Yeah.
Just to clarify, so delete 8 is not delete the number 8.
Correct. Well, delete at 8. Do you see that? Okay. It's a sequence operation.
Position,
yeah. So this is very important that you differentiate between sequence and set semantics, right? If I'm dealing with the sequence, I better not be looking up intrinsic things on this data structure, right? Because it's not an intrinsic data structure. It doesn't support that. So if I wanted to find the, say, the index of key 8 or something like that, right? Then all I could do is, it's similar to like an array. I would just have to loop through the whole sequence and tell me if the thing's in there, right? Can't really do better than linear time. This data structure is not designed for that. What is it designed for? It's designed to find things by their index in the sequence, right? So how do I find the 8th index? Well, I mean, I'm looking at the tree, and I can just, count along the in-order traversal. What's the in-order traversal, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, found 8. But what does a sequence AVL tree do, right? I'm storing subtree sizes, and when I'm here, I don't know what index I'm at, right? How can I find out what index I'm at? From the root. I look at my left subtree, see how many it is, right? There are 7 things here. 1, 2, 3, 4, 5, 7, 8. Right, yeah, because I'm looking for the 9th item by index 8, right? So this is saying that I'm the 8th item, right? I'm the guy at index 7. Does that make sense? Because I'm looking at the subtree size here. So what do I know? I know that the index that I'm looking for is to my right, right? So I go down over here, and I happen to know what index of am I looking for in this subtree? 0, right? I want the first thing in this subtree. My search index has changed now, right? Because I essentially dealt with all of those 8 items, right? So here I'm looking for the 0th thing in my index. I look to my left. If I didn't have a left subtree, I would be the 0th thing, right? And I would return me. But there is stuff in here, so I'm looking for the 0th thing in here, right? Which is just him, and I return it, okay? And actually what I'm doing is I'm deleting it, right? So I delete it. Yuck. What's the problem here? They're not height balanced. What's not height balanced here?
The left subtree is, or sorry.
So this guy's not height
Right
balanced, right?
subtree of the right.
This guy's subtree is not height balanced, right? This guy's 2, this guy's 1. Okay? So how do we fix it?
Rotate.
We do some rotations, right? This is actually the bad case, the third bad case that we talked about yesterday, right? If I tried to just left rotate this guy, what would it look like? It would put 12 here, it would put 10 here, and 8 would be attached to that. No, it's height balance wrong in the other direction, right? That's no good, right? So the way to handle this case where I'm badly skewed to the right, but my right subtree is skewed to the left, I have to do a rotation here, right rotation, and then do a rotation. So that's the formula, okay? So here we first do a right rotation at 10, okay? Which gives me something that looks like 8, 10, okay? Well, obviously this is not better than what was before, but it's an intermediate step so that we can fix it, right? We right rotate here, and then we left rotate here, right? The default is that we would left rotate here, but because this had the skew in the wrong direction, I need to right rotate this one first, and then we can do it. So now I rotate all of these guys over, right? And put 12 down here, 8 here, 10 here. Done. Everyone see that that's what a rotation looks like? Okay, it takes a little while to get your mind wrapped around what the transformation is, but hopefully you guys all followed that transformation. There was a little magic while I was trying to draw. Yeah?
I still don't feel like this tree is height balanced.
It's not. Good observation. Why is that? This thing still has height 3. What is the height of this thing? 1, right? This is height 1. And actually, when I was doing that rotation, I needed to update all these augmentations, right? Which augmentations did I really need to, which subtrees have changed during those things? I don't remember what the thing looked like. What did the thing look like? 10 had 8 in its subtree, so its subtree definitely changed, right? 8 subtree changed.
All of it changed.
12 didn't change. Eventually.
It used to have 10 and 8.
Mm-hmm.
And now it has none.
Okay, so there's the case analysis that's in your lecture notes and was done in recitation, right? It tells you that these A, B, C, D kind of subtrees, right? The ones that could change in these things, those subtrees don't change. The only subtrees that change during one of these fix operations, when you do 1 or 2 rotations, is either 2 nodes or 3 nodes whose subtree has changed. Here, it could have been the case that 3 subtrees have changed, right? But in the easy case, only 2 nodes, X and Y, I think, in the nodes could have changed. And so when I do that, I have to recompute their augmentations from their augmentations of their children, but it's only a constant number of those, so I just recompute them because the subtrees below me haven't changed, right? Okay, so we have a height mismatch here. Yeah.
Can you please explain why the 12 12 used to be where 8 is currently in, 2 kids and then 10.
Right. So originally, in the picture, 12 has a bunch of things in its subtree, right? 10 and 8, and we just deleted 7, right? So its subtree definitely changed. There used to be 3. Oh, no, sorry, it did, right? Yeah. So here, 3 node subtrees have changed, but that's actually the most. I'm showing you the worst case, right? Only 3 nodes possible in doing one of these double rotation things could have changed their subtrees, and so we just have to fix the augmentation of those 3 things. In the easy case, it's just 2 things, okay? All right, we have a unbalance. How can we fix this? I could have been mean, right? I want to be able to right rotate here, right? To rebalance. I could have been mean and switch these 2, right? If I switch those 2, then I'd have to do 2 rotations to fix this thing because the middle one is heavier than the left one against what I'm doing, right? But I'm not that mean, so I'm going to right rotate. How do I do that? Well, right rotate at 6 is going to bring all of this down below 4, right? And stick this subtree as the left child of 6. Does that make sense? Yuck, that's going to be fun to draw. I'm just going to redraw it. That makes more sense, right? 4, 11, 3, 2, 1, and then 6, 5, 9, 8, 12, 10. That's the right rotation at 6. Is everyone cool with this? The rotation, my x is 6, my y is 4, right? I have A, B, C subtrees, right? What I'm doing is kind of switching which of x and y is the root here, right? So now y is the root, and B and C subtrees here now become the children of x underneath y. And notice that hopefully through all that process, my in-order traversal has not changed. We had to update our augmentations along the way, but it's a constant every time we walk up the tree. And we walk up the tree only a logarithmic number of times. Yeah? Yes?
Just checking. So every time we do a rotation, we just like update the augmentation immediately afterward before we do any other rotation.
Exactly. Yeah.
Second part. Updating the augmentation just means like updating like the count and the height, just the properties that stay.
Yeah, basically what we did, we defined, when we augmented, Professor Demain yesterday defined for you what a subtree property is, right? It meant a property that I can compute only by looking at my children, the augmentations of my children, recursively, right? So here, instead of trying to increment or try to think about locally what this augmentation should be, I'm going to throw away my old augmentation and just recompute it from my children, because those recursively better be correct. Does that make sense? Yeah.
So just looking at how the rotation works, right? I'm having a little bit of trouble wrapping my head around. So basically, you're swapping 4 and 6, so that way 4 becomes the parent node, and 6 becomes the right node.
I'm going to draw this picture. It's just something you got to memorize. This is X, B, C, and A. Can you see that picture? Okay. What? Yeah, it's in your notes. It's not a big deal, right? But if you've got this structure where X has a left child, right? And these subtrees may be empty or not, doesn't really matter. What I can do is I can move from here to there, has the same in-order traversal order, right? But it's got a different shape. And in particular, subtree heights have changed, which means it can help us rebalance the tree. And that's the whole point of AVL. Does that make sense?
And that's the right rotation.
This is a right rotation. This is a left rotation. Any other questions? Yeah.
So for updating the augmentation, so like how many nodes do you have to update in that case? Would it just be all the sectors?
So as I'm walking up the tree, every node I might have to fix with the rebalance, but that rebalance does at most 2 rotations. And there's at most log n ancestors that I have because my tree is height balanced, right? At 2 log n or something like that, right? Which means that at max, I might have to do 4 log n rotations, right? Because each one could do 2 rotations. Does that make sense? Now, in actuality, you can prove that in a delete operation, it's possible that you have to do a logarithmic number of these rotations up the tree. This was that bad case. This is called, the original tree I gave you is called a Fibonacci tree. It's the highest height balanced tree you can have on a given number of nodes. The fewest nodes for a certain height. You can think of it either way. And if you generalize that to a large enough thing, then that thing will take a logarithmic number of rotations going up. Now, actually, with an insertion, you can actually prove, you can go through the case analysis. an insertion operation will always rebalance the tree after one rebalance operation, which could include 2 rotations. Does that make sense? Yeah.
So the right rotation, you become like the right child of your previous left child, right?
Yeah, so in right rotation, this guy becomes a right child.
Yeah, so can you not, like, are there certain rotations that you can't perform depending on whether you had a child?
Yeah, so if I didn't have a left subtree, can't perform a right rotation there. Yeah, so a right rotation necessitates that I have a left child, so if you're doing it, and you'll see our code actually checks to make sure you have a left child, right? That's an assertion that you might want to fire before you ever do one of these rotations. Anything else? Yeah.
Just to reiterate, so an insertion may take 2 rotations at most to fix.
Mm-hmm. A constant number of rotations, and a deletion could take a logarithmic number of rotations. Now, that's not something you need to know. It's not something I'm proving here to you. Just something that's interesting. There are rebalancing schemes, like in CLRS, right? They introduce a red-black tree to introduce balance. And those trees actually have a weaker bound on, it's not as tightly height balanced as an AVL tree is. It allows higher than skew too, right? And because it's kind of a weaker restriction, they get away with only doing a constant number of rotations. They can afford that before they fix the tree. But a little more complicated.
Is that a PhD lesson?
Very nice. Okay, any questions on this? Okay, so so this is more of a mechanical question you'll get on your problem sets. And now we get more onto the theory type questions. These are going to be reduction type questions. Okay, so this first problem, Fick-Nuri. This is anyone? Nick Fury, right? So it's an Avengers reference. So basically what happens in this thing, he's got a list of superheroes that each have an opinion on whether they should go fight Thanos. Okay? And their opinion can be strongly positive or strongly negative. And so what Fick is trying to do is find from among his Revengers what the log n most extreme opinion Revengers are, so that he can talk to them. Right? He doesn't want to talk to everybody. He wants to talk to a logarithmic number of them. Okay? It's kind of whatever. All right. So basically, we have a classified situation where you're given as a read-only input data store of these things in an array, okay? And I want to find the log n ones with the strongest opinions. Does that make sense? And I want to do it, and the first problem is in linear time. Okay? So you actually don't know how to do this yet. You'll know how to do it with material that you cover in, they teach you one way to do it in 046, but we're not going to get you there right now. We'll teach you another way to do it on Tuesday, right, which is via binary heaps. Okay? Binary heaps are an interesting thing that implements a subset of the set interface. Okay? Really, it just, you can build on some iterable x, okay? I collect a bunch of things. These items have keys, right? It's a key data structure in the same way. It's implementing what we call a priority queue interface. I can build these things. I can insert things, but I'm not going to do that here. All I really need here for this situation is a delete superlative kind of operation. In this case, probably max. Delete max. Okay? So this is like I got a data structure, right? I'm calling these things. Does that make sense? Yeah.
What's a priority queue?
Yes, a priority queue is essentially something that implements these two things. Actually, there's a third one where I can insert a new thing, right? But I'm not going to need that right now. So that's what a priority queue is. And actually a set, this is a subset of the set interface, right? Right? The nice thing about a heap, which I won't show you how it's done, right? But what a heap can do, so if I had both of these operations implemented using a set AVL tree, how long would these things take me? How long does it take to build a set AVL tree? N log n, right? Because essentially, I'm getting a sorted order out of this thing, right? If I'm inserting these things one at a time, right? Or I could sort them and then put them in a tree in linear time, like you saw a couple days ago, right, in recitation. But I have to sort them at some point, right? I need to take at least n log n time, because if I'm going to be able to return their order, their traversal order in linear time, and I have this lower bound of n log n on sorting, I kind of needed to spend n log n time here, right? And how long would this delete max take?
It's sorted so long.
Log n, right? So it's a set AVL tree. Where is my max? It's the rightmost thing. I can just walk down the thing, take it off. Maybe I have to rebalance. But that's a log n operation, right? It's the same as like insert last in my subtree, right? So for a set AVL tree, this is n log n, this is log n, right? Now, there's another data structure that does better for one of these operations, and the same for the other one that we've learned earlier. Anyone remember? Set AVL tree didn't actually give us anything over a sorted array in a dynamic array. Okay? So what that did, right, was we could sort it in n log n time using merge sort or something like that. And then we could just pop off the last one n times, right? That would be an amortized, if I didn't care about taking up that size, I could do it in worst case constant time. I just read off the last one. I don't need to resize the array ever, right? I can just ignore that. Does that make sense? Okay, but that's, okay. If I had a data structure that implemented these two operations, can someone tell me an algorithm to generate fixed list? Don't worry about running time right now, but that just uses these two operations. Yeah.
So we built this data structure. It's ordered from least to greatest for absolute value.
So don't worry about where things are ordered or anything like that. I don't tell you how these things are implemented, right? All I'm saying is I can accept a bunch of these things, and I can remove the maximum and return it. Okay?
Yeah, anyways, just build it. Make sure that you build it such that the opinion levels are the absolute value of the opinion levels.
Sure. Okay. So that's a nice thing. What I'm going to do, as your colleague is saying, is I'm going to look through all of the things in my input. I'm going to copy it over to some writable memory store. Okay? Right? That read-only thing is not relevant to this part of the problem. Right? What I'm going to do is right. Sorry, I'm thinking about your problem set that we're writing and mixing it up. Okay, so we copy it over to our new linear size array, right? But instead of putting their values there, I'm going to put the absolute values of their values. Does that make sense? I just check if it's negative. If it is, I put the positive thing there, right? Okay. And then I stick that array in this build, right? I put that there, right? So that'll take some, whatever this build time is. And then I can delete max k times, or I can delete max some number of times, however many things that I need, right? If I want log n highest things, I can just do that log n times, right? So for this, if I had such a data structure, I could do this in one run of this operation and log n runs of this operation. Does that make sense? I could solve this problem reducing to this data structure, right? Now for a sorted array or a set AVL tree, right, this operation kind of kills me already, takes n log n time, right? The nice thing about a binary heap is it does this operation in linear time. You will see that on Tuesday. And it does this operation in log n time. Okay? So what's the running time if I use a binary heap to implement this data structure? Order of n times order log n times log n. How big is log n squared, log squared n compared to n? It's smaller, right? So if I add those two running times together, it's still linear, right? Okay, so that's how you solve the first problem, okay? I didn't have to tell you what a binary heap was or how it did what it did. All I needed to tell you was that it did this operation in linear time and it did this operation in log n time, okay? Yeah? All right. The magic will be shown to you on Tuesday. Part B says, now suppose fixed computer is only allowed to write to at most log n space. Well, okay, that's a problem here, right? Because before we copied over the entire array, filtered it out, right? And then did some operations, but we couldn't even afford this if we couldn't store the whole thing externally in writable memory, right? Okay, so we can't do that. So in some sense, this is a more restrictive environment, right? I can do less things than I could. It's less powerful than my previous situation where I had as much space as I wanted to use, right? So it kind of makes sense that I maybe couldn't get the running time bound that we had before, right? Maybe I have to sacrifice something because I'm in a more restrictive computational setting, right? Okay. Now, this is something you could solve with binary heaps, but you don't have to. You could solve it with set AVL trees. Does anyone have an idea of how you could solve this using a set AVL tree? I'm limited by my number of my space is at most log n. Yeah?
Wait, so how much space does a set AVL tree take?
Right, space, right? There's constant number of pointers for each one of these nodes, right? And I'm storing in nodes and space, right? Basically, every data structure we've shown you takes space the order of the things that we're storing, right? It's not using additional space. It might take more time to do certain things, but the space is, takes the number of items that we're storing plus maybe a constant factor, right? Right. So I'm going to draw my input here, which I can only read. I can't write. Do I give it a? I'm just going to call it A. Okay. So this is my list of all the Revenger opinions. Okay. I can only read it. But my computer can only write to this logarithmic amount of space. What can I put in that space?
The log n greatest.
Well, I can certainly put log n things in there, right? Okay. So if I'm given that restriction, I probably want to build a data structure of that size, right? Containing that number of things. That makes sense? Because what else are you going to do, right? Okay, so I gave you an idea. Maybe we could use a set AVL here, right? I see a logarithm in my answer, right? It's very possible that we might have, sorted arrays, right? Or set AVL things. Those things give me a log somewhere in my running times, right? So kind of makes sense that I might have maybe a set AVL tree here. Why would a set AVL tree be helpful for me? Yeah.
Because it's sorted and have the traversal order, you can calculate the traversal order and insert things inside of it pretty easily. Sure,
I can do all of those things, but in particular, it's going to help me be able to find a large one quickly, right? If I kind of have a set of things, it's going to be, and I'm maintaining this data structure by adding things incrementally to it, right? I can find out what the biggest one is, or the smallest one, pretty fast, right, in log n time, right? So if I have log n things in a tree here, right, what's the height of that thing? Log n. That looks familiar. So what can I afford? I can afford a linear number of set AVL tree operations on this data structure, right? Okay, you had a question?
I forgot.
Okay, I'm sorry. Yeah.
For an AVL tree, does it have to be a BTS tree?
It BST, right? So when I talk about someone likes Korean K-pop, okay. BST, but in natural kind of in the lingo that you're probably used to hearing in other contexts, what we mean in this class is a set AVL tree, right? Now, sometimes what people refer to as a binary search tree doesn't have balance semantics, right? So we might call in this class a set binary tree, right? But really, they're useful because they're balanced, so we're going to usually just assume that we're talking about balanced things here. Now, a set AVL tree has these binary search tree semantics where the keys are ordered. These items have keys and they're ordered. It's a set interface, right? Whereas we also presented to you a sequence interface, right, for which these things don't even have keys. How could I store set semantics there, right? So, but that's the distinction that we mean when we say binary search tree versus really a set AVL tree versus sequence. Yeah?
So if we were going to make an AVL tree out of this, would that mean that like when we make a node, we tell it like we are keying on the absolute value of the like?
Okay, so when you're making a set AVL tree, you got to tell us what, if you're storing objects, you got to tell me what their key is, right? If you're just storing some numbers, like what I'm doing here, right? Now this isn't a set AVL tree, right? But if I'm just storing numbers, I have to tell you the items that I'm storing are the keys, okay? And then everything follows, right? But if you've got an object that you're trying to sort, like the students in this room, you got a lot of properties, right? I want all the people with phone number, right? Maybe I want to key you on phone number for some reason. Maybe that's going to help me find out where you live. This is getting a little, I don't want to go there. Okay, so but if I give you a set AVL tree, I got to tell you what it's keyed on. If I give you a sequence AVL tree, right, it's obvious what my traversal order is going to be because I'm giving you a sequence, right? That's what the input gate was, right? Does that make sense? All right, so I've got this set AVL tree of size log n. What should it be keyed by? Absolute value of their preference, right? Or of their opinion. I don't remember what this is called. So, but what log n things do I put in here? I don't know. I don't know anything about these things. What makes one better than another, right? Let's just put the first log n things. That make sense? All right. What could that tell me? Now I've put this thing in. How long did that take? Log n times log n time, right? But that's much less than our running time, right? So that we're looking for, so I don't really care, right? I mean, I want you to say how long it took, but for my purposes, I know that it's lower than the running time I'm looking for, so, and I did that operation once, I don't really care about it anymore, okay? Yep.
How did you get log n times log n?
Because the number of things I'm storing in this thing is log n, and so if I pattern match the build time of an AVL tree, and I stick log n in there, right? Then it's log n times log n.
Gotcha.
Okay.
So is that just for one iteration?
Well, right now I've just built this thing, right? I just built it once. I'm asserting too that maybe I don't need to build it again, right? What could I do instead? So right now I know I haven't filtered my data at all, right? I'm just storing these things in sorted order in some way, right? What can I do to maybe start processing the rest of the data? Yeah.
Well, when you like
try to scroll through the list A and try to like we find someone that's bigger than like try to keep the maximum.
Kind of sweep this guy over, inserting things, and always maintaining. You know, if I do that and I keep sticking things in, I'll have this sorted thing at the end, and now I can just read off the biggest k things, right? However, as I'm inserting things across here, my thing's growing.
Well, just delete the smallest.
Oh, delete the smallest one. I like that idea, right?
Just basically replace it.
Yeah, basically replace it, right? So what I'm going to do, here's a proposal. We're going to take the next guy, stick it in. Awesome. Which one don't I care about now? The smallest one there. So kick the smallest one out. Now this one that I stuck in may be the smallest, right? So I just kind of passed it through this thing. But how long did that take me? Took me the height of this tree. What's the height of this tree? Log n, right? So I put one in, I pop one out. That's the smallest, right? And I keep doing that all the way down the thing. How long did that take me?
Oh, about time to get through the rest of it. So, about times log.
Yeah, I'm processing n minus log n things, which is basically n, right? And each one of those operations took me height of the tree time. So that gives me the running time that we're looking for, n log n. Yeah.
It's like reminiscent of like a sliding window technique.
Yeah, it's a kind of a sliding window technique. You may have been using one recently. Okay, everyone okay with this? Yeah.
Can you just remind me of the context that we're talking about this log n like tree and like where?
So this thing, the size of this thing is log n.
Yeah.
I mean, sorry, log n, and the height of this thing is log of the size.
I'm sorry, but like in relation to like our little like log n size like bite right there, like are we sticking this full of small log n trees or like how?
No, so sorry, I'm taking this stuff. There's no intermediate data structure here. I'm just sticking all these things into a BST. I mean a set AVL. Yep.
Well, it's one.
Into one set AVL, right?
Okay.
Of size log n. I'm sticking a guy in, popping the worst guy out, right? Going through all the things. I need to make sure when I'm sticking it in, I'm keeping track of which revenger it is and that I'm taking the absolute value and all those nitty-gritty kind of things. But that's the basic idea, right? I'm just taking this, I'm sliding the window in, putting something in, taking something out that may or may not, probably is not the same thing. And at the end of this procedure, right, the invariant I'm maintaining here is that my thing always has the k largest opinions of the ones that I've processed so far, right? That's obviously true at the beginning when I build this thing. And when I get to the end, I've processed all the things, and this has size log n, and so I have the log n largest, highest, extremist opinions, and then I can just do an inward traversal of this thing and read and return. Does that make sense? And I've only used logarithmic space. Okay? Yeah.
Wait, so I don't get it. Are all the opinions in that AVL tree?
Are all the opinions in that AVL tree? All of these opinions are in the AVL tree. And at some point, I will insert every opinion into this AVL tree, but I'll be removing the ones that I don't care about as I go. Does that make sense? I'm always maintaining the invariant that this thing, before I insert something, has exactly log n items in it. And then I'm maintaining that invariant by sticking one in, taking one out.
Oh, okay. So then which one are you deleting?
Always the min, right? Because I'm wanting the largest ones.
And the min by absolute value.
But yeah, exactly.
Okay.
So I'm keying by the absolute value of these opinions. Yeah?
Could you go to that total runtime?
Total runtime here, right? It's bookkeeping, right? So it took me log n times log log n time to build this data structure at the beginning, right? Plus n times log n. I did, basically n operation asymptotically n operations this way. It's actually n minus log n operations, right? And each one of those operations, tree operations, doing one insert, one delete, each one of those took the height of the tree time. And so this is that. Good? Yeah.
If instead of blindly just insert and delete,
Mm-hmm.
if you do a comparison, and then...
So the inserting and deleting, a set AVL tree is actually doing comparisons within its data structure.
Just compare with the min.
Sure, you could do that,
And then,
right? Right, so I could do it the other way, right? I could remove the smallest element here to start with, right? And then I compare it with this guy, and then whichever is bigger, I stick it back in. Same thing, right? It's just, am I doing the delete first and then the insertion, or am I doing the insertion first and then the deletion? Any other questions? Lots of questions. All right, well, I'm probably going to have to skip the problem. We're going to move on to SCLR. All right. What's the reference here? Yeah, CLRS, right? So these are 4 academics who wrote a popular textbook in computer science. Okay, this is the same kind of K kind of thing. Okay, they found K first editions and they want to auction them off. People can go onto their website. They have a bidder ID. It's a unique identifier, right? And they can place a bid for one of these books, right? And they can change it during the bidding period, but at the end of the bidding period, the academics want to know who what is the expected revenue I'll get by selling to the K highest bidders. Does that make sense? Yeah? Okay, so note that before I build this data structure, I know what K is. K is a fixed thing, right? Right, because my running time of this get revenue depends on this K. It's not an input to that operation, right? So K is kind of, I don't know what it is a priori. It could be n over 2. It could be log n, right? It could be 1, right? But the data structure I build needs to satisfy these running time properties no matter what choice of K that the academics told me. Does that make sense? Okay, so what I need to do is as time is going on, people are placing new bids and updating their bids, right? And those updates can take log n time, but as soon as I close the window, I want to be able to tell in constant time, right, what the K highest bidders are. Any ideas on how to do this? What are the operations that I have to do? I have to be able to place a new bid, right? Associated with a bidder is an ID and a bid, which is also an integer, right? How many dollars I'm going to pay for this book. Update the bid. In some sense, I need to find whether that person placed the bid before, right, in my data structure. So at some point, I'm going to need to find on bidder ID. Does that seem plausible, right? So I might want to have some kind of dictionary on bidder IDs, right? When I say that I want to have a dictionary on something, right, I'm not specifying to you yet how I'm going to implement that dictionary, right? What are my usual options? A hash table, but what if I need worst case time? A set AVL tree, right? That's going to be your go-to for a dictionary, right? Because that's going to give me log n time to find things by a key, right? It's the only thing, except for a sorted, you could also use a sorted array, right? But that's going to not be dynamic. And here we're updating who's in my data structure all the time, right? People are going in and placing bids, right? New people placing bids. So my set of things that I care about is changing all the time. So that's probably going to steer me away from sorted arrays because they're not good with dynamic operations. Okay, so I'm going to need some kind of dictionary on bidder IDs. But I'm also going to need to maintain the sum, right, of the k highest bidders. Does that make sense? Right? And so in some sense, I need to keep track of an ordered notion of the bidders, right? The bids that are in my data structure. Does that make sense? Right? So order is going to be important on the bids. I'm going to need a lookup on bidder ID. And that's about it, right? Okay, yeah?
Just checking, so something that's worst case runs at worst case time runs in expected that same amount of time, but not vice versa.
Yes, correct. Yeah, so that's a very good observation, right? If it runs in worst case time, it also runs in expected that time, right? Because there's essentially no randomization that I'm talking about here, right?
Or in worst case, it runs in time.
So there's a stronger notion which we want you to specify, which that actually there is no randomization here. We're not using a hash table, right? In this class, that's the only situation where that's going to be an issue, right? But if it is, what this problem is saying for each object state, whether your running time is worst case expected and or amortized, what we're really trying to get you to say is evaluate the running time of your algorithm with the proper qualifications, right? If it took worst case, I want you to say that it took worst case. If you used a hash table, I want you to say expected. And if these operations were sometimes really bad, but on average they're really good if I did a lot of them, that's amortized, right? Right? Or if I reduced to using a dynamic array, right? Or if I reduced to using a hash table, those dynamic operations would still be amortized, right? Okay, so the dynamic ones. Nice thing about linked data structures is that dynamic operations aren't amortized, right? So we're going to be able to get. Now, for this problem, we can actually get worst case bounds. So we're going to try for that. You can also do it in expected using some hash tables for that dictionary, right? Okay. So when you approach a data structures problem in this class, you want to tell me what it is you're storing, first off, right? Tell me what's supposed to be in those things, right? Some invariants on this data structure to, make sure that when I do queries later, right, that these things are being maintained, right? So that, if I have, if I'm maintaining a sorted array, right, and I'm supporting an operation to find the maximum, anything I do to this data structure better be maintaining the invariance that these things are in sorted order and the last thing has the maximum item, because my max return thing is going to look there and return that. Does that make sense? So I want to tell you, you want to tell me what is being stored at a generic point in time during your data structure, right? What is being maintained so that when I support a dynamic operation or a query, right, in a dynamic operation where I'm inserting and deleting things from this thing, I need to make sure that I'm maintaining those invariants. And when I'm querying, I can actually rely on those invariants to answer my query. Does that make sense? Okay, so for this problem, this is 43. Okay. Any ideas? I have two kind of keys that I might have to deal with. One's a bid ID and one's a bid, right? So how could if I have two keys, right, that I might want to maybe order on one and look up on another, how many data structures do you think I'm going to use? 2. That's a pretty good guess. Okay. So one of them, let's just guess, right? Like I need to be able to look up on bid, right? So let's store these bidders, right, in some kind of dictionary that's going to be able to look up those things fast, right? So, 2 data structures, right? One is a dictionary on keyed on bidder ID. Okay? What else am I going to want? What's up? The other way around, a dictionary stored on the bids. Is a dictionary what I want here?
Set up ABL tree. I think the more
I want to maintain order somehow, right? Because I want to maintain the k biggest things that I've seen so far. Right now, if I had at some point in time, right? What's going to happen, right? If I'm maintaining the k largest at any point in time, it's possible that one of those bidders maybe decreases his bid, right? So it's no longer in the highest. I'm going to also need to keep track of the other guys to see who I should add back into that set, for example, right? So here's an idea. I'm going to keep not just one other data structure, but two other data structures. Maybe this is a leap. You don't have to do this. There's a way to do it with just one other. But I'm going to store two more. One is a kind of a data structure to store bidders with store the k highest bidders, and a data structure to store the n minus k highest bidders. Does that make sense? So this separates my problem quite nicely, right? If every time someone does an interaction with this data structure, right, I can check to see whether it's bigger than the smallest thing in here, right? If it is, I can do the same kind of trick I did before, right? I can remove it and stick my new one in there, right? And but I removed it, I have to maintain this property, right? So I stick it in here, right? There's another case. What's the other case? It's smaller, right? In which case, I don't do anything to this data structure and I just stick it into here. Does that make sense? Right? So what are the operations these data structures need to maintain? Finding the minimum or the maximum of these two sets. Does that make sense? Really, where are those operations? I don't have them anymore. But they were the priority queue operations. They had delete max, right? And also insert were things that it did well on, right? So any priority queue, right? Anything that can deal with maxes and mins, right? Is good, right? And what's a data structure you know that can deal with maxes and mins pretty efficiently? The set AVL, right? So set of data structure here, I'm going to say set AVL. And obviously it's going to be keyed by bid, right? Because that's the thing that I'm going to want to find maxes and mins over. Okay? Everyone following the logic here of why I'm maintaining these things? So this is the level of invariance that I want to maintain, because when I go to, for example, do this query, get revenue, right? I can just run through and sum all of these things. Oh, wait. How much time do I have? Do I have k time? No, I don't have k time. So I can't afford to sum up all of these things at the end of my, right? I have to return it to you in constant time. Any ideas? Yeah, just compute, update a sum, right? Along with this data structure, I'm going to keep a fourth thing, which is just total of their bids, right? I'm going to call it like a T, okay? And that's something I'm maintaining. It's part of my data structure, right? You can think of it as I'm augmenting this thing with a number, right? And the point of augmenting this thing with the number, right, is that I can just, if I need to know what the total of this stuff is, I can just look at that number. Does that make sense? All right. So now I think, we're almost done. We're basically done, right? How do we do this? Someone walk through to me how I would get revenue with this data structure. I basically kind of told you, look at this number, return it, right? Because that's the invariant that I've maintained on my data structure. I'm relying on this invariant. Now, I better make sure this is good when I do dynamic operations, right? I make sure I maintain it. But if I, by induction, are ensured that all of this stuff is good, and when I do a dynamic operation, all that stuff is maintained, then I'm all good, right? So get revenue, after I kind of did all this extra work, right, is very easy. I just look at this number and return it, okay? So when we're grading a data structures problem, usually we give you some points first for setting up your data structure separately from the operations, and then we give you points per operation that you successfully deal with, and then some points for correctness and running time. Yeah? You had a question?
So would total be like a thing that we update whenever we like mess around with the highest bidder tree and then n minus k highest bidder tree?
Sorry, say that again?
So like, are we treating like the total like sort of like an augmentation that we update every time we do something?
Yeah, yeah.
Okay.
So it's just one number. It's not really a data structure. It's just one number that I'm storing with my database, right? Okay? All right, so how do I implement a new bid operation? Yeah?
Just one question. Can we assume that the bids will also be unique?
Can you assume that the bids may be unique? No. Right? So that's actually something that is a really useful observation. We've been talking about set data structures as requiring unique keys, right? How can I deal with non-unique keys? It actually turns out that, hash table, it's really important that these be unique keys, right? Because I need to check whether it's in there. I'm looking for that single key, and when I find it, I have to return, right? If I had multiple things with that key, I might not return the one that I'm looking for, right? It doesn't even make sense, right? But you can generalize the set kind of infrastructure, right, to deal with multi-sets. How can I do that? Well, with each key, right? Again, I'm storing unique keys. With each key, I can link it to a sequence data structure or any other data structure, right? And what I'm doing is anything that has that key, I'm going to stick it in that data structure, right? So instead of storing one item there, I have the possibility of storing many things there. Now, I have to change the semantics here, right? If I'm saying find on this key, well, now I could say I'm going to return all of the things with that key, or I'm going to store something with that key, right? But you get the idea. All I have to do is map it to some other data structure to maintain those things. Like maybe I want all the things with that key. I want to find the one with this other key, right? So maybe I link to a set data structure that can search on other things, right? But the idea here is we maintain this uniqueness key property, right? I have to relax my semantics so that I'm storing multiple things at that key location. Does that make sense? Yeah.
Why does it matter whether the set APL tree has unique keys or not?
It does. So it's going to matter here, right? Because I have bids, right? And the bids could be non-unique, right? Two people could have the same, bid, and by our definition of a set data structure, it had to have unique keys. So if I stuck in all these things keyed by bidder, we got a problem, right? Now, in actuality, we can get away with that by storing basically a linked list of all the things with that key, and we'd be fine, right? And then whenever I want to return one, I could just do. But actually, a binary tree, right, actually is flexible enough that in most implementations you can just store a bunch of those things, but actually our runtimes do worse than, right? What does it mean to find next in my sequence, right? What does it mean to return the next larger thing above this key? Doesn't really make sense because there could be multiple ones. Which one do I return? And if I repeatedly do find next on this data structure, right, I might not loop through all the things, right? So some stuff breaks down in our interface, right? So I would prefer you use unique keys in this kind of situation. Next Tuesday, I think with binary heaps will deal with non-unique keys. That's fine. But if you're going to use non-unique keys in here, you just got to be a little bit careful about the semantics. Okay? Yep.
But in that case, if multiple of the same key are stored in a linked list, how would you argue runtime for like finding something?
So you get the same running time. You have to change the semantics on what you mean by find something, right? I just want to return anything with this key, right?
What if everything has the same key?
Then it takes constant time. I just return the first thing. I mean, these are special cases that, you have to think about, right? I don't like thinking about them, right? So I just like having unique keys. And if I want a situation where I have non-unique keys, I'm going to basically put collisions at that key into a new data structure, right? It's just easier for me to separate out in my head on what's happening. Because all of the running times that we proposed, very strong definitions for unique key, when you're dealing with a multiset, it's a little bit more problematic. Any other questions? We really need to kind of move on here, right? Dictionary keyed on bidder. We still haven't implemented any dynamic operations. New bid, what do? What am I going to need for my update? I'm going to be able to need to essentially find in each of these data structures where that bidder is, right? And if I just have a thing keyed on their bid, right, the interface doesn't tell me what their old bid was. It just tells me what their bidder ID is, right? So if I just had their bidder ID and their new bid, how the heck am I going to find out which of these data or where in these data structures they are, right? What I can do is I can store in this dictionary, which I can look up in some amount of time, right, a pointer to where it exists in these things. Does that make sense? This is called cross-linking. You may have done that a little bit in problem set 2 or something like that. Yeah?
Are we storing a pointer to a specific bidder?
Yeah, exactly, right? So the invariant we have is that all of the bidders we've processed so far exist in these data structures, right? In one of these data structures. And because we've used a set AVL tree, right? In particular, it exists in a node of one of these data structures, right? What we can do is, in this thing, maintain pointers, right? Mapping each of the bidder IDs to their location in these data structures. And why is that going to be a useful thing, right? Say I map this dictionary, right? What could I use for this dictionary to get the running time we're looking for? I could use a hash table or a set AVL, right? If it's set AVL, I'm going to get logarithmic time, worst case. With a hash table, I'm going to get constant time, but it's expected, right? So it could be linear time in the worst case, right? So we're going to use a set AVL tree, right? Because that's what we do right now. And that's going to give us worst case, okay? So what I'm going to do is, for each one of these things, I'm going to store that pointer. So what I'm going to do is, first, I'm going to do that operation we had. If I'm adding a new bidder, right, I'm going to take the D and B, right, these two values, that object, that bidder object or whatever. I'm going to look at the smallest thing in this data structure, right, see if its bid is bigger than the thing I'm inserting, right? If it is, then I'm not going to touch this data structure. I'm just going to insert it in here. And now, after I insert it in here, I know exactly where it is in the data structure. I just inserted it, right? Right? So now, holding that in my hand, the node, right, I can go and insert that bidder into here, right, by bid ID, right? Which is also going to take logarithmic time. And now I can store with that node my pointer to this data structure. Does that make sense? And in the other case, I kind of do the same thing, right? If it's bigger than the smallest thing here, I pop that smaller thing out, stick it in there, and I stick my new guy in here, cross-linking each of those pointers along the way. Does that make sense? Hopefully. Kind of? Kind of? Okay. Yeah. And for update, very similar, right? If I want to update a certain bidder, I look in this data structure, find the bidder, traverse that pointer to wherever it is in one of these AVL trees, right? If it's in this one, I just remove it from the tree, right? Or I remove it from the tree and then I reinsert, right, with whatever the new bid is, right? And if it's in this one, again, I remove it from the tree, reinsert in whichever these things is, and then I might have to, swap a constant number of things back and forth here to maintain that this has the k highest, right? And when I do those dynamic operations, I'm always removing some constant number of nodes in each of these trees and adding back in a constant number of things. And while I do that, I just make sure to update this total as I go, right? This total was the sum of all of the bids in here. And if I insert a new bid in here, I have to add to that total. And if I remove one, I have to remove from that total. But again, it's a constant number of things I'm moving in and out of these data structures. And so I can update this in constant time. Does that make sense? Now, the lookup here and the insertion and deletion into here, those each took logarithmic time, worst case. But I did a constant number of them. So again, logarithmic time. Does that make sense? That's essentially this problem. It's difficult, right? There's a lot of moving parts here, right? But if you just break it up into describe to me you really do a good job on this part, describe well to me what your data structure has, then those descriptions of those algorithms can be pretty brief, actually, right? So, in this one, you tell me these three data structures, you tell me this guy's mapping to its location in these things, I'm maintaining this guy, right? And then you just maintain those things with dynamic operations and then use those things for query operations. Does that make sense? Okay. Wow, we have 10 more minutes. I'm going to briefly do 404, okay, for you, okay? Receiver roster, we've got a coach. She's got a bunch of football players, receivers. And wanting to start on our team, some number of players that have the highest performance, okay? And by performance, we mean the average number of points they've played in games that they have logged in their system, right? But actually, their data is incomplete, right? They don't know which games and how much they scored and all of these things. There could be errors, right? And so these interns, they're constantly updating this database with queries like, never mind, this person didn't play in this game, or actually they did and they scored this number of points, right? That's the clear and record things, right? And then at some point in time, right, like when we want to play a game, right, I want to be able to return the jersey with the kth highest performance in log n time. Okay, this is kind of a rank query, right? The kth highest. Okay. Now in actuality, I might want to return all k highest players, so that might be my roster, right? But this is a more generalized query. It's more specific, it's not really comparable, but you get an idea for why that might be useful to the coach. I don't know, maybe not. Okay, so what's the idea here? We have a lot of different things floating around. We got games, they have IDs, unique IDs. We got receivers, they have unique IDs. And each receiver could play in many games, right? Oh, it's kind of worrisome. And many receivers could play in the same game. These kind of many-to-one mappings are a little confusing. And then we've got each player, receiver, having a certain number of points per game, and we're trying to sort them kind of by their performance, which is a rational number, right? Which has to do with the number of games they've played and the total number of points, right? Now, I see rational number, I can't compute that, right? That's what we were talking about last problem session, right? But what I can do is I could store the total number of games they played and the total number of points they had, right? And you could imagine by augmentation similar to this, right? Every time I add a game, right, one of these small operations, I can update that information for each player, right? Right? If one of these dynamic operations is affecting only one receiver, I can, update whatever it is in constant time, probably, right? If I just store with the player what their total number of games is, as recorded by the database, and how many points they've scored. Then, if I have a data structure that needs to sort the receivers by their performance, so I might be able to find the kth one, right? The kth largest, then I can't compute that performance, but what can I do? I can compare two players based on their performance using cross multiplication, right? Right? Because I have the numerator and denominator of each of these rationals, and I can cross multiply and figure out whether one's bigger or smaller. And as long as I have a comparator, I can do set AVL stuff. Does that make sense? Okay, so that's I'm just going to outline kind of the components of this data structure. Okay. Well, first off, I'm going to need to record a receiver, and a receiver could have a lot of games. But this is kind of a receiver-centric kind of problem. Does that make sense to you guys? Right? I'm not ever wanting to filter on all the receivers playing a game, right? I'm never removing a game from the system. I'm removing a receiver from ever playing in a specific game. Does that make sense? So if I'm storing a receiver and each receiver has some games associated with them, kind of makes sense I might want to have a nested data structure, right? Where maybe I have a dictionary on receivers, and for each one, I store all the games that they've played in some other data structure, right? With each receiver, I store its own data structure containing all its games. Does that make sense? Okay, so that's the idea, right? We have some kind of, I need to be able to look up receivers, right? Because I'm clearing them or I'm recording them, right? So I'm going to have a dictionary, or here I'm looking for worst case log n time. So I'm going to skip the dictionary abstraction and go straight for the set AVL. AVL keyed on receivers, I before C, E except after C. That's good. It is I, EI. Okay. That rule never works. Okay. Set AVL tree on receivers, and each one of those nodes, right, with each one of those receivers, I'm going to store for each, store a set AVL on games. Okay? Why do I store a set AVL on games? Why don't I just store a list of all the games? Because if I want to remove this game from a receiver, I need to do that in log n time. And here what we're saying is that n is the number of games, but that the number of receivers on the team is always less than the number of games. So, right? If I search in this AVL tree and I search in its AVL tree, I can be assured that those two searches was only log n time. Yeah? Because I need to remove a game, right? So there you go. Then, what am I doing? I'm returning the kth highest performance. Well, with each one of these guys, I also store, what was this augmentation? The sum of the points stored in these games, right? Sum of points. And, what was it? Number games. Because if I store both of those things in constant time, I'm going to be able to compute their performance, right? Or I'm going to be able to have the data I need to compare performances. Yeah.
You just store them as like variables.
Yeah, it is. It's just numbers, right? These aren't data structures. This is data structure. These are just numbers. Okay? And I'm storing that with each receiver, right? But that's not going to help me find the kth highest player, right? None of these things are sorted by performance, right? So I need a last data structure. Five. I need to store something dynamically sorted by performance. Set AVL, yeah. Set AVL, storing receivers, keyed on performance. Now, when I say keyed on performance, you want to mention something about the cross multiplication, right? Like I'm storing with each one of these things this augmentation, and when I'm comparing two things, I'm using cross multiplication. But other than that, then we can abstract it away, right? You've abstracted that function call, and I can imagine comparing two keys, I can do this, right? This is a theory thing. I'm not asking you to implement that, right? But that's sufficient for me as a reader of your solution to be able to say, yeah, you know what you're talking about. Okay? All right. So how do I connect these things, right? The thing is I'm going to need to be, I need to update these things, right? When I insert or remove a game, right? So how do I know where these receivers are in this thing? I store a pointer into this data structure, right? So up here, I store a pointer, right? To where it is in the data structure, right? Again, I'm storing all the receivers. This has the same size as the number one data structure up there, has the same number of receivers, right? But we're not quite done yet. Because I'm not wanting to know like who has the best performance, right? I want to know who has the kth best performance. Ugh. How do I find the kth best thing in this tree, right? I've got a tree, right? Set AVL tree, it's mapped on performance, right? I know where the last one is, but if I want to find the kth one from the end, how do I do that? It's an AVL tree. A set AVL tree, all I'm storing is heights. Is there an operation that you've thought about?
You're not storing the size of each.
Ah, a set AVL tree by default does not store sizes, right? That's what a sequence does. But you think maybe that would be helpful in this situation, right? Yeah, so actually, if I decided to augment by sizes also, I could do the exact same kind of sequence find at operation, right? And I could be able to look up the n minus kth item, right, in here, using the exact same function for subtree at that I had in the sequence AVL tree stuff, right? So actually, in CLRS, they don't even bother with sequence AVL trees, right? They go straight to, if I wanted this rank find functionality on a sorted order of things, right, then I could augment with subtree sizes, right? But it's actually a much more useful general property, so we decided to present it to you in the context of sequence AVL trees, because then I can just basically reduce to it when I get to here. Okay, so that's kind of a structure of a data structure that will work on this problem. I leave it to you as an exercise to implement all of these operations for yourself or take a look at the solutions. The last one is going to be put online, the solution. It's pretty complicated. It's what's called, you can think of the size augmentation finding rank as a one-sided range query. It's basically how many things are to the right of this value, right? What the last problem does is walks you through a two-sided range query, right? Where I want to know how many nodes are between these two values, okay? So it's a walkthrough. All right, thanks guys.